Hello everyone. This lecture I'll be explaining multiplicative functions, and it's called the Dirichlet's product, and I'll explain some properties about it. So I begin here with making a definition of what is called an arithmetic function. Basically here it's a function that takes a natural number and outputs any number. Could be a complex number. Uh, so this is basically an arithmetic function. Then we have a more specific definition, which is the multiplicative function. Say here we have an f. So f is multiplicative. So this, if it happens, if f1 equals 1. So so the first condition, f is arithmetic. And here I would say it belongs to like a curved A, so the set of arithmetic functions. So this is the first condition. So the second, that f of 1 is equal to 1. And the third, that we have a product of two coprime numbers, then we can distribute the function. So like that. But this has to happen only if n and m are coprime. So this is basically the multiplicative function. We can see some examples of multiplicative function, like is d, which is the n example. So this is the number of divisors of n. We can list the first, for example, 10 elements of this function. So here we have one divisor, here we have two, we have two, we have three, we have two, we have four, two, 1, 2, 4, 8, so here's 4, here's 3, here's 1, 3, and 9, here we have 4, and 2, here we have it's 2, so here we have 6 dividers. So the 12 has the divisors 1, 2, 3, 6. And the 4, yes. 1, 2, 3, 4, 6, and 12 itself. All of these are the divisors. And as we can see here, for example, the 12, it's like the product of 12 equal to 3 times 4. So we have the d of 12 is actually d of 3. Which is this value here times d of 4, which is this value here. And we can find the same pattern, for example, with the 10. So it's the product of this value and this value, and so on. So this is the number of divisors. Another one is the sum of divisors. So this is the sum of divisors function. So the divisor 6 to 12 is 8, 1, 2, 15, and the 9 is 1, 3, 9, 13, 10, 10, 15, 12, 15, we have 14, and 7, and 2, and 1, so it's 24. 12, this should be 28, I think. So it's 1 and 2 and 3, that's 6, and 4 and 6, so that's 16, and we have the 12, which is 28. So I assume this is correct. So as we can see here, so example, the 14 is 2 times 7, and if we multiply those two numbers here, so 3 times 8 is actually 24. That's as expected. Also, we have here the case for the 12, which is the product. So 12 is 3 times 4. And here, if we multiply those two numbers, we actually find that it's 28. So it's still the same property satisfied. And here also is the same. The way you can prove this for these two functions. So then we have some number n, which is written as in the factorized forms like that. So actually, it's to count the divisors of n, it's more here of a combinatorial problem. So it's as if we want to find n, or numbers of n, which has the power here alpha 1, alpha 2. So here we must have like those primes and nothing else, because any other prime that would be an m, it wouldn't make m divide the n. So we have to restrict ourselves to these primes. And also the alpha, each alpha has to be less than or equal to the corresponding e here. So alpha I is 0. And pi. So the number of so this m is one possible divisor, and when we choose all the possible values for the alphas, then we get all the possible divisors. And here we can see that each alpha is independent from the other one. So each alpha has only this constraint. So here we can choose any alpha in this range, which has a length of ei plus 1. So it's all the numbers from 0 until ei. And basically, we will multiply this for all possible choices. So this will be e1, e2 plus 1, and so on. En plus 1. So this can be k just because there's an n here already, just to make it less ambiguous. So this is basically the number of divisors of n. And as we can see, it's a multiplicative number. Because if we have two numbers that are like co-primes, then it means they have two distinct sets of prime numbers. And basically, we just multiply the exponents plus 1. So here, for example, we can actually divide it like this. So here, the divisors of this number is actually this value. The divisors of this number is this value. So here we can always distribute the the number of divisors functions across the co-prime factors. So here we can see that the number of divisors is a multiplicative function. And the same would be for, if we call sigma a10. So this is the sum of divisors. Here it's the sum for all d, such that d divides n. So d to the power of k. So it's the sum of the kth powers of the divisors. I'll just prove it for k equal 1, and the argument is easy to generalize after that. Also, if we have n to be represented like that, okay, yes. So the sum of divisors, here we can write all the summations here. So here we sum all the powers of P1 from 0 until E1, and we make this product. And it's the same for P2. And so on. If we notice this like big multiplication, what it basically does, it's also, you can see it from a combinatorial point of view. So it's as if we're making all the combinations of some powers of P1, and we are adding them together. So this expression is to try every number here, to multiply it with every number here, to multiply it with every number here, and so on. So this will be just a big summation of P1 to some power alpha 1, and we choose the alpha from alpha 1s from 0 to E1, and we multiply this until yes. And here all the alphas are still bound in this constraint. So this very big product is basically a product for all the possible combinations of powers of the p's. So here all the alphas are still in the same constraint as we had here in the number of divisors, this constraint. So here basically this is the sum of all the divisors. So basically this proves that also, as we can see, that we have the sum of divisors of n, and it can be split into some independent products, and each depending only on the prime. So still here, it's we could separate the functions for co-prime multiples. So this is what we have here. And basically we can just generalize this for the kth power by making, instead here of P1, we can just put the powers that we want. And this would be basically d to the power of k. And it would be also here. No, sorry. It would be here, and here, and so on. So that's it. So these were two functions that were multiplicative functions. Then we go to the next definition, say so the summation of f over the divisor. So this, if we have an arithmetic function f, so we say the sums of f is equal to the sum over all divisors of f of. So this is just a definition here. And we have two theorems, which I want to prove. So the first one, that S of SF is multiplicative if and only if f is multiplicative. So this is one theorem. And the next one would be this. I think we could already see the pattern from here. So it says, like, if we have a multiplicative function, so this summation of it can be written as like summation for each prime divides n. So here we can go from I equals 0 until the like ek for some prime k. And this would be the summation of the kth prime raised to the power 5. And basically this summation, we would have a product of it for all the possible primes from 1 to r. So this is our function. This is given that n is equal to the product from k equal 1 to r of pi. So basically that's it. So we have this sum of functions over divisors. So it's divided like that, and this is how we can calculate. And I think let's see that. No, it's not. Okay, then we move to the next point, which is the Dirichlet product. Okay, so the Dirichlet product is defined as, we have two arithmetic functions, f and g. So it's defined with this O operator. And this expression, when we apply it to, so this is the argument of this new function, f composite g. It's not composite, f product g, or here the product is the Dirichlet product. So this is defined as the sum over all divisors n. We take here f of d, and here the g of n over d. So here we can see that, for example, n, let's say, is equal to 12. It has the divisors 1, 2, 3, 4, 6, and 12. Then n over d will basically reverse this, right? So that's it. So this is what we have here. So basically you can see that you can also write this the same as the summation over d, and we can just swap here the arguments. So it's f over n over d times g of d. Because here when we go through all the d's, so the n over d is just is the other number here, and we can see that we are looping over all the pairs that has the product equal to 12. So it doesn't matter what which order we do that, but still, as long as we get all the pairs. So from here, if we notice this expression is actually equal to g dot f. So here we can see that the Dirichlet product is commutative. So then we go to the next point. We also prove that the Dirichlet product is associative, meaning that we have f dot g dot h. We exclude this first and then this. It's the same as making this. So this will be equal to all divisors. So we'll have three numbers that has the product equal to n. So basically this is how we define this triple product, double product. So this will be f of d1 times g of d2 times h of d3. We notice that this expression here is that you can write it in two ways. We can write this as this d3 okay. So yeah, so d3 has to divide the n, and then the summation of d1 times d2 equal to n over d3. This is f of d1 times g of d2. And all of this times h of d3. This is one way to write this product, and if we notice, this is the first expression that we have. That's this part. Because here we have this is equal to summation, like I will call the d3 to be just d. So d divides the n. And here we have d dash, which would be the d1 here. So all the numbers that divides n over d. Here we have that this is f of d times g n over, sorry, n f of d dash, and here's f of n over d dash. And all of this times the h of d. So as we can see here, that this part is basically the like f dot g of n over d. So So this is the expression we had at the end. Dash. And this is basically is equal to hd times f product g to this function of n over d. This over all the world. And this we get by the definition here, from here. So basically this shows that we make the f dot g and then we make it n dot h, and this will be the same if we also make the order in the different way. So the argument for this is basically we're just going through all triples of numbers that are a product that lead to some certain product. So for example, if you want f of g of h, we're just going to, let's say, of 12. We're making all the possible divisors. So here 1 and 12. And here we can make 2 and 6. And 4, 3. 6, 2, and 5. So here this was always 1. Then we can put the d1 to d2. We have 1, 6, or 3, d2. And we have 1. This one 4. As you notice, all of these are combinations that all the possible combinations that would have a product equal to 12. So basically, if we find, like, because these are all the combinations, so if we swap any of the divisors, we still get the same combinations at the end, but just in a different order. And since we are making a summation for all the different tuples here, so the different triples, so it doesn't matter for us which order we get these triples, as long as we get all of them. So this is like another like intuitive way to think of it, why it's associative, and it doesn't matter which order we use to execute this. Okay. So now we proved that the operator is associative, and the last thing, so all of these were just for arithmetic functions. So the last thing I would prove for only the multiplicative functions, that if we have f and g are multiplicative, I would say they belong to curved M, which means the set of multiplicative functions. So in that case, the Dirichlet product is also a multiplicative function. I can prove this here. So we have n times m, and n and m are coprimes, so we can make this as the summation over all divisors of f f of d times g of n over d, or n times n. So here every divisor of n times m, we can write it as d as a product of two divisors, d2, d1 and d2, where d1 is a divisor of n and d2 is a divisor of n. Because here n and m are independent, I mean they are co-primes, so there are no shared divisors between both. So basically when we get all the divisors of n, all the divisors of m, and we take all these possible combinations, it will basically get all the divisors of d. So using this, so just a quick demonstration of this would be if we want to factorize the, let's say, so the 12. So the 12 is a product of two distinct co-prime numbers, so 3 and 4. So here we have the divisor 3 and 1, and here we have 1, 2, and 4. Basically, you can just make every combination here. So 1 times 1, and here 1 times 2, and so on. 1 times 4, and 3 times 1, 3 times 2, 3 times 4. So these are the 6 divisors of 12. So here we use this substitution. So this is equal to d1 that divides n and d2 that divides m. F of d1 times d2 and g of n over d1 times m over d2. And as you can see, because d1 divides n, so this is an integer, and d2 divides m, so this is an integer, so this is all is an integer. So this summation is, we can use the multiplicative property here. I'll remove this layer soon. So basically this expression that we have here, so we continue from there. So it's d1 that divides n and d2 that divides m. So here, because d1 and d2 are also co-primes, because they divide co-prime numbers, so they also don't share any divisors, so we can make it like that. d1 is f of d2. And the same for this part here, so d of n over d1 times g of m over d2, and the summation is still the same for d1 and d2 with the same constraint here. And here we can, so this part here and those parts here, we can combine them using the multiplicative property. So this is a summation like over d1. So as we can see, this is a double summation here for all the combinations. So I will write it as a double summation. So this part here is equal to f of n. I'm sorry, no, I'll just do it f of d1, n of d1, and here we have f of d2 times g of m over d2. As you can see that this part here doesn't depend on d2, so we can take it outside as a constant here. So basically we have d1, the summation of d1 over n, so f of d1 and it's g of n over d1. And this is multiplied by with this here. This is d2 that divides m. F of d2 as you can see inside the first summation, we still have all this expression inside. Now we'll do the same trick again. Like this summation, all of like this term here actually doesn't depend on d1, so I'll get it outside this whole summation here because it's a constant with respect to this summation. So basically this will end up having the equation d2 divides m this, all this expression divided by this expression. Sorry, multiplied by this expression. F g n over d1. So this is the expression that we have, and as we can see that this is actually the f dot g of n times f dot g of n. So if we just go back a bit, so we see that this is actually the summation that we want to. So it's f dot g of n times m. Just move this here. So basically this is equal to this expression, and this is equal, we decompose it, the divisors here, like in two independent divisors. So this, by the way, is a double summation because we sum over two independent variables, so d1 and d2. So this expression is equal to this, and then this will decompose it using the multiplicative property. So if we see this here, we decompose it into this and to this, and putting these next to each other, end up having this expression. And then here, because this one has only d1, so it doesn't depend on d2, so we can take this as a constant outside to end up having this summation inside of this expression. And with respect to the d1, this here is a constant, so we can get it outside also. So we end up having this expression, which is equal to this. It's equal to this. And as we already know, so this from the beginning is f of g of n times n. So here we prove that if f and g both are multiplicative, then f to g is multiplicative. So if both of f and g are in M, then we have g belongs to M. So this is what we call the closure property. It means if we have so the closure under the multiplicative function. So if we have some multiplicative function and another multiplicative function, and we make the Dirichlet product, so still the output is another multiplicative function. So we never get something out of this set. So here, then, so I hope that the people notice the pattern so far. So I'm just looking for some axioms about the Dirichlet product, and it's actually quite similar to the group axiom. So here I just proceed to the last part. So I define some multiplicative functions. So there's the I of n, which is equal to 1 for any possible n. And there's the identity function, which is equal to n for all possible n. And there's the e function equal to delta 1n. So no one knows this expression. It's this expression will equal to 1 if the upper index is equal to the lower index. So basically if n is equal to 1 and 0 otherwise. So here if we take a look of, we have some arithmetic function. If we take the product of f dot e, so this is the summation over divisors f of b times e of n over d. And all of these e's here will be 0 unless d is equal to n. Unless this expression is equal to 1, so basically this is equal to f. So here we can see that the e here is as an identity function for the Dirichlet product. So e, we have this. F. So the one last thing remaining is to find an inverse. So we will define an inverse in the standard way. So we have f should be times this inverse should be equal to this, equal to our identity element e. So here I'll put this. So I'll put this definition here. So we'll expand this. So this is f dot f inverse of n. So we have this. So I prefer to write it in the other order. This is f n over d times f inverse of d. This is equal e of n. So in this summation, if we exclude the last term here, so d that divides n, and d is smaller than n. So here we exclude the last divisor. F inverse of B. In this, we add the term that we excluded, so we just get it outside of the summation. So it's F of 1 times F inverse of N. This is equal E of N. So we can see here, we can get a recursive formulation for F1 for F inverse. Basically, F inverse of N is defined, so it's E of N minus this summation, and B is smaller than N of F N over B inverse. All of this is divided by F1. So here we have the inverse defined, and we can see that this is a recursive definition. So the F inverse of N depends on all the F inverses of lower functions. So there's some divisors of N, and also the divisors has to be smaller than N. So this is a recursive definition, which is well defined, and we have the base case for it. Actually, you can see that F inverse of 1. So this will be E of 1, which is 1. And this summation is empty, so it's 0. And then we divide by F of 1. So as we can see, if we have an arithmetic function with the condition that F of 1 is equal to 1, then we can define a unique inverse function that belongs to. So the F inverse will also be an arithmetic function. So here we make so I think we have all the group axioms now satisfied. So So here we see it's commutative. So this actually, we only need this condition to prove it's an abelian group. And from here, this we have it's associative. And here we have an identity function, an identity element, sorry. And here we have a definition of the inverse. So basically we have all the conditions of the axioms. So here we can say that the set of arithmetic functions in the Dirichlet product is a group. But here we have to make it A1, which is so the arithmetic functions that have F of 1 is not equal to 0. Because actually this part here was a bit wrong. So it's not wrong, but we can even have a less tight condition. So we just need that F of 1 to be not equal to 0. This we don't have it here. So this we only need because otherwise the inverse wouldn't exist, because we will have a division by 0. Otherwise the inverse will exist. So this, and we have also that set of multiplicative functions is a subgroup with the Dirichlet product. So this we know because the set of multiplicative functions is a subset of the arithmetic function, and it also had this condition, because here we have always f of 1 is equal to 1, and there's another condition we need to check to make sure this is a subgroup. So we have here the sub. So the multiplicative functions is a subset of the arithmetic functions, and also we have the closure property. We prove this. So this we prove here. So it was this big proof. So if the f and g are in M, so the product is also still in M. So this is the closure property. So we need to make sure here that so we already know that there is a closure for the set M, so we know that this can form a subgroup. And actually, they're also, both of them are abelian groups, because the product operator we have is commutative. So if we reflect also on last thing, so if we check back this expression, so the sum of for a function over the divisors that we had earlier. So this is f of d. This is actually is equal to the product of f with I, where the I is always equal to 1, so we can think of it as if we are always here having I of n over d. That's why this expression is correct. Also, we can define later on what's called the Möbius function. This is given mu, so this is defined to be the inverse of I. Right. I think it's the inverse of E. So I will explain this in a lecture later on, but so actually I think it was the inverse of I. So we'll check that in the next lecture. So in the next lecture, I will be explaining the Möbius function in details, how to calculate it and how to use it in the Möbius inversion. We'll also explain a little about the Euler-Torsion function and why it's multiplicative and so on. So this was it for now. So thanks for watching.